Okay, good afternoon, everyone. So we're very happy today to have our own Urs, who is going to tell us about quantum channels as quantum state monad transformations. This is part one, and part two is going to be on Wednesday. Urs, please.
Right, thank you very much. Yes, exactly. That's the title I'm going to give. Very basic introduction to the most fundamental aspects of quantum probability theory, a bit of quantum channels. The reason why you're not seeing the title on the screen is I'm just showing the webpage and the draft that I'm taking this off. This is a project we've been working on with David, Mitchell, and Hisham since a while now. You may remember I gave a similar, as you will see, colloquium talk maybe a year back on quantum gates. So this is kind of now quantum channels. And back then, I may have mentioned, I forget how much we talked about this, that the motivation for looking at these basic, very basic constructions of communication is really just an unitary operator. These very basic notions, quantum mechanics, and reinvestigating them is because we were looking into the question of how to best formalize basic quantum physics in a way that lends itself to be formalized in programming language. So the idea is, Mitchell has, as he presented even earlier, this linear version of homotopy type theory, and the broad idea is, although it's far ahead, is to realize this is a universal quantum programming language and to see how inside such a context of linear homotopy types, that's why we have linear homotopy types on the slide here, how inside such a context we can very naturally talk about all the fundamentals of quantum physics. So that's the idea of these monads. There's a general principle, which I'm going to be talking about next week, not today, that if you have some programming language and you want to enrich it by what's called effects, so you want to have programs to have certain side effects besides their usual program. For instance, the side effect of having a measurement outcome in a programming language. The mathematical structure that encapsulates this is called monads, monadic effects. And so the idea is today I'm going to be talking about the very basics, no quantum programming, no type theory, nothing. The very basics of quantum theory, really, mostly from von Neumann's 1932 article, almost 100 years ago. Just recalling and setting up the scene, and then next week the idea would be that I show that all this structure that von Neumann back then dreamed up kind of follows rather naturally from some very fundamental aspects of quantum programming theory if one does it in the quantum context. All right, so that's enough of an introduction, and I'm just going to jump into the kind of review section of this manuscript we're building here. And so I don't have slides in the usual way, but I have these, I think, pretty printed formulas, except this one. I just noticed it's not so pretty printed, but that happened just in the last minute. So there's some space missing here, but we'll get there. So I'll just jump to the section, quantum probability and quantum channels, and I'll just explain. And for some of you, this will be completely basic. Some of you may not have heard it again before. That's why I don't want to go through it. We want to just talk about the basic constructions of what is a quantum state, what is the probability of measuring something in a quantum state, and what does it mean to transmit information through so-called quantum channels that is contained in quantum states. And so this just to recall, the most fundamental thing, it seems a bit silly now to say this after having had all these talks on quantum physics, which of course all presume this, but let me just highlight, because it's going to be an important point, that the probabilistic aspect. So I should say, when we were talking about the quantum gates last time, we just want to say, okay, here's a Hilbert space of qubits, or here's a space of qubits, here's another space of qubits, and we just want to implement a CNOT gate between them. Then you do not need to talk about Hilbert space structure. You're just looking at a complex vector space, and you have a linear map between them. And you can combine these and tensor them together and build quantum circuits. So what one might call coherent, not statistical, not undisturbed quantum circuits that do exactly what we think they should do without any noise, without any measurement effects, just deterministically evolve the wave function. For those objects, for those structures, one does not need the Hilbert space structure, just a complex vector space structure. The point I want to highlight here with this first broken formula is that it is the Hermitian inner product on this complex vector space, which is very tightly connected to the probabilistic interpretation of quantum physics, which of course is a thing, rather remarkable, that connects the formalism to actual physical, to actual observable reality, because it produces actual probabilities that can be measured, or with which certain measurements are going to be obtained in the laboratory. So just to recall, and this is a subtlety I'm highlighting here, which involves or concerns us in formalizing this. It need not concern us so much now, but an important point of the inner product on these complex vector spaces, you all know, of course, but it's kind of a remarkable aspect anyway, is that as opposed to an inner product on a real vector space, the inner product on a complex vector space, the Hermitian inner product is not a bilinear form, it's a Hermitian bilinear form. So it's a complex linear map as shown here, not from vector space H tensored with itself, but tensored with its complex dual space. And using that, yes, please.
So why do you say it has to be tensor with its dual space?
Sorry, I didn't understand.
So why do you have a tensor structure of each cross H?
Yeah, so that's what a bilinear form is. So an inner product on a real vector space is a bilinear map from two copies of the vector space to the real numbers. And a bilinear map out of some vector space or a pair of vector spaces is the same thing as the single linear map out of that tensor product. The tensor product is, in a sense, defined in such a way as to make that statement true. It's the universal object. So the bilinear maps vector linearly through it.
But do you think, like,
so this just means, you know, we'll see the formulas in a moment. So H, our Hilbert space H, is the one that contains our quantum states, psi, and H stars, or the other one, is going to contain the dual states, and we just pair them. So you'll recognize the formula. If this seems unfamiliar, you'll recognize the formulas that you know from your textbooks in just a moment, right? So this inner product, besides being sesquilinear, which was the content of the previous formula, complex linear second argument, complex antilinear in the first, as we have Hermitian, positive, and non-degenerate. So this means that, yeah, so here's the property of, you can pull out a complex number of the second argument, it just comes out. But if you pull it out of the first argument, it will come out complex conjugated due to this rule, which is the hermiticity rule on the sesquilinear product, or inner product, that if you switch the order of the two arguments in the inner product, the result gets complex conjugated. So there's very subtle and not a priori obvious interaction here of complex conjugation of complex numbers with probability theory, which a priori is not something you would expect, which is part of the reason, I think, why quantum physics was so, maybe still is, so surprising to the founding fathers, because there's something going on here, which you would not have easily guessed, unless maybe you look a bit deeper. That should be the point of the next talk. But here we just take this historical development. So there's the conditions, and it's going to be very useful to stick to this classical physics trick here of denoting, you know, giving the situation. We say, okay, so we always pair vector with a dual vector. So we're just going to break this inner product in half, denote the actual elements of our Hilbert space, of our vector space, by this half inner product notation. Okay, and then the other ones, so the linear maps, so by this non-degeneracy condition, every element in the linear dual space is obtained by forming the inner product with another element. And so we can form this operation, forming the inner product with some element. We just omit the dash here and write it like so. It's actually funny, I went and looked up for citation purposes, the original source. This is actually a publication, like this is not a remark, this is actually a dedicated publication by Dirac in 1939. He says, I propose to write things this way, and it got published. If there's nothing else than to write it this way. But anyway, this is now a completely standard notation, and we're going to see, especially maybe next week, that this is actually quite useful. So, first example that will play a major role in, you see, this is completely elementary here, but it's actually important maybe to look at these foundations. The most immediate example, which play a major role, especially for the measurement process, is the case where we build such a Hilbert space just by forming direct sum over some set of copies of the complex numbers. So the set of copies for me will always be called W. This is for worlds, possible worlds, many worlds. Anyway, it's just some set. And for my purposes, it's always a finite set. And in general, I'm just entirely focusing on finite dimensional Hilbert spaces. The point being not that things, not that there would be any problem in going to infinite dimensions, everything works, but it adds extra technical subtleties that would have to keep carrying around, which add nothing to the probabilistic points we want to make here. So we just ignore this. You just have to keep in mind that some of the formulas I'm showing need some adjustment. For this naive direct sum formula, you have to write differently if you have an infinite dimensional Hilbert space. But for a finite dimensional Hilbert space, we can look at this direct sum. Well, and then the elements of the set that we're spanning the space with declare to be the basis vectors by just putting this cat notation around them, of course, forms a linear basis of the space, and we can make an Hermitian inner product by just declaring that to be an orthonormal basis, so that the tensor product of the W's with each other is just 1 if they're the same, and 0 otherwise, and the rest, if you have some complex linear multiple of those W's, the rest of the inner product is determined by the Hermitian rules.
So like just a question.
Very good.
Is it mandatory for this Hilbert space to have the multiple copies of the same state? So can they have different states?
Yes.
So like, as we know, like psi evolves to some psi prime and psi double prime and so on.
Are you asking whether it's necessary that I have always a copy of C here?
Yeah.
No, it's not necessary. This is the simplest example. You have direct sums of index sets of Hilbert spaces, and in fact, that's what one generally has and what we are after. But this is the most elementary example. Yeah, I'm trying to keep it really elementary here. So here's a first, as some of you would have seen in school, and some of the first fact, or one fact that is nicely expressible with this notation now, and which plays a major role in the foundation of this theory, is that we have a compact closure or self-duality condition or whatever, or just duality condition. Anyway, we have this relation that if you have two Hilbert spaces, H and H prime, or just, for the first line, there could just be any complex vector space. For the second line, I'm assuming this you're equipped with the Hermitian product. You form the linear space of linear maps between them, which, following some category theoretic or type theoretic notation, I'm denoting by this lollipop notation. So this is just the Hom in complex vector spaces, the internal Hom in complex vector spaces from H to H prime. The set of linear maps from H to H prime equipped with their evident vector space by argument-wise multiplication. So what this little example here exemplifies is that for H being a finite dimensional vector space, that set of linear maps is the same thing as the tensor product of the codomain vector space with the dual of the first one. And a good way to see this using this bracket notation is that if you have a linear map here that takes, it's sufficient to define it on these basis elements, right? So I'm assuming our H is of this form above. If it takes W to some linear combination indexed by W of the other W primes, then it's the same thing as just this Ket-Bra notation where we're just manifestly exhibiting the matrix. This is the most elementary calculus, but that's going to be used a lot. Is another actually historically interesting point. So I also hunted down the origin of the Born rule, one of the foundational axioms of quantum physics. And it's interesting that, so it originates, of course, with, well, not of course, but in this case, actually, it does originate with Born. And it's interesting that because before von Neumann, kind of in his book, Foundations of Quantum Physics, which in the German version is from 1932, actually nails it down. It says, quantum physics, probabilistic theory, where probability sees are given such and such, Born and all the others who followed him, and this includes Dirac, if I remember well, and also Schrödinger, and big names, they all, one has to say in hindsight, kind of fail to see the full substance of this discussion, at least if one judges from the way they write about it, because they all write about it in footnotes. The Born rule originates in a footnote, and it keeps being discussed in footnotes. So people think they have more interesting things to discuss, and in a footnote they say, "Oh, by the way, here's some probabilistic interpretation." And it was only von Neumann who really saw that something really profound is going on here. Then it says, you all know this, but it's worth amplifying. This is the crux of what makes quantum physics what it is and strange. So it says if you have a system which is in a state psi, so it is an element or represented by an element of this Hilbert space, I'm assuming now it's normed, so it's in the unit sphere of the Hilbert space. That's this S notation for sphere. Then we can ask, okay, we have this system sitting here, right? It might be some quantum dot or some whatever quantum system. We have somewhere. Well, I mean that's a big assumption, of course. But suppose we know what it means to measure the system and ask whether it is in one of the actual classical states that span the Hilbert space. Whether, for instance, we have a qubit state. We might have a spin in some atom, an electron. We just measure the spin, whether it's up or down. We would have this two-dimensional Hilbert space. The states would be W would be 0 and or plus and minus, and we could measure this electron. Is the spin up or is it down along a fixed given axis? And so it might have some wave function, some state now, and the probability to find it in state W is by the Born rule. This expression here, so it's the inner product of a given state psi with that basis state, which corresponds to the classical element, the classical basis element that we're measuring. And we take the complex modulus squared, which by the rules of Hermitian inner products, we can equivalently express in either of these forms here. So this is supposed to be a bit, some people call this, just this inner product, the transition amplitude, probability amplitude, as opposed to the actual probability. It's a complex number in general. It kind of tells you, yeah, whatever it is, the amplitude for psi to go into W. That is not the probability, strangely. The probability of actually finding W is kind of you have to multiply this with the amplitude of going back from W to psi. And by the rules of Hermitian inner products, that means you take the complex modulus squared of that expression. Yeah, so that is one of the foundational laws of physics, really, meta law, if you wish, that law just holds in all experiments. And yeah, just to note that, yeah, my page breaks broke here a bit. Just to note that it is again the actual definition of an Hermitian inner product that makes this definition an actual probability distribution, right? For this to be an actual probability distribution, this assignment probability in set psi, the W occurs. So first of all, this has to come out to be a number between 0 and 1. Well, it's a real positive non-negative number by the fact that it's this complex square here. But the fact that it's actually lower or equal to 1 is an instance of the Cauchy-Schwarz inequality, which is of course it's a standard statement, but the proof requires like 5 or 6 lines, so it's not a completely obvious, or it wasn't completely obvious maybe before Cauchy proved it. So this is the consequence of the laws of Hermitian inner product, and it serves to make this expression related to probability distribution, which I think is on a philosophical or maybe epistemological level kind of remarkable, because we're connecting probability theory here to something that a priori did not look at all like it would have anything to do with it. And then similarly, the fact that these probabilities sum to unity, let's just look through this for those who haven't seen these kinds of computations. So we want to know that if we sum of all possible measurement outcomes, this probability is that in step psi we do measure W. Well, by what we just said, we have to sum these complex squares by the rules of hermiticity. We can express it like so. You see now it's actually important to write like so. Psi goes to W, goes back to psi, because now we realize, see, everything is linear here. So we can take the sum inside there, but this thing is now the matrix, which, you know, when it eats a W, it spits out a W. So under this identification that we had here, this is the matrix that corresponds to the identity matrix. So to the identity map. So we see that we're just inserting an identity, so we can remove this term and we get psi by assumption that we run this unit sphere that is 1. And so we have a probability distribution. So let's skip over something here that's important for something else for us today. And now, so this is okay. So this was just basically how the Born rule, how there's any probabilistic aspect of quantum physics. And now we want to get into this idea of mixed state. So we say, okay, so if we have a system, we know exactly it's in. So this is the curious thing, right? We know the system is exactly in state psi. The curious thing here is it is thought, like, there's no evidence that it's not true that this psi isn't the complete description of this reality. You might say, well, if there's, if you can only tell me the probability to measure W in state psi, then probably you don't actually know your system completely. If you would look closer, you would probably be finding some hidden degrees of freedom, and would be, if you measure them, if you understand them, you would be able to tell me exactly which measurement outcome we're going to obtain, not just with which probability. But this does not seem to be the case, for all we know. There's really no indication that it's any different. So there's this curious thing that having an exactly known state of the world, and nevertheless only gives you a probabilistic, probabilistic description of what you'll actually see. Well, okay. But now we say, okay, let's embrace this. So if that is the case, what if in addition, I don't actually know which state I have? What if there's in addition some classical uncertainty? So what if I don't know, is it this quantum state, the system is in or that? So this may happen for thousands of reasons. That is the default that actually happens in any case, in a laboratory and everywhere. The system might be not at temperature equal to 0. So then there will be some thermodynamic fluctuation. Or you have an insufficiently prepared measurement apparatus. You don't actually, it doesn't actually produce exactly the state you think it produces. There's some diffusion. So for thousands of reasons, we may not actually know exactly which state the system is actually in. And for Neumann in 1932 said this. Well, I think there's already, he just went through this, let's do this, let's do that. But there's already an important point here, which one should highlight, to observe that these super elementary things, which you could teach in high school if you wanted, there's some subtleties in here, because you would say, okay, if I don't know, if I want to combine classical probability with this quantum physics, what I probably want is a probability distribution on H, on the underlying set of H. I want to say, with such and such probability density, this vector. Or maybe if you're more sophisticated, you say, no, it's not just H, it's just the unit ball and maybe the projective Hilbert space. So you might say, okay, I want a probability distribution of this. It's just all the possible states. And if I don't know which one it is, then. But no, this is not what one does. One says, no, we want a probability distribution just on any linear basis, normal linear basis for the Hilbert space. So just on the classical measurement outcomes. I mean, all these things don't, once you work with them, they seem very natural. And just to highlight, that there is at these very foundations here, there is some steps that are not, that you wouldn't, and people didn't guess if you weren't told to do this. And part of the next talk is, I don't want to oversell it, but we will see some of these things emerge from. Anyway, so for now it says, okay, so if we don't know which measurement outcome and which state the system is in, let's have a probability distribution, PW, on these things. And then in just a half sentence, von Neumann says, oh, by the way, it's actually convenient, let's write like so. And he says, let's consider a matrix. So if I have, if somehow want to arrange these PWs and with the information that they correspond to these classical states. So let's form this matrix. It's the sum over W's of this projection operator on the W's eigenstate weighted by this probability. Right? So it's clear this is a thing you can do. Or convert that into this equivalence. It's a linear map, right? That is defined on base elements by taking W to PW times itself. So what is the point of this? Well, so this is how von Neumann actually motivates it then, because then we have the following formulation. So we want to say now the following. Suppose I have this probability distribution. And so I want to say my system is in either of these basis states, W, but I don't know which one necessarily, depending on the distribution. But it's with some probability. Then what is the probability that I will measure it in some state W prime? Well, so the total probability is now combined of two things. There's a classical distribution, classical contribution. We do not know in which state, or we don't know in which state our quantum system is. So, but we know with probability PW, it's in state W. And in that case, we know if we measure W prime. So this notation is a bit misleading now. W prime is with respect to another basis W prime. Otherwise, this would be right. So maybe I should have used different letters here. I mean, W prime could be W, but then it's not so interesting. So suppose if this system prepared in some measurement base, and now you're asking for measurements in another base, which is like in Stern-Gerlach or something. You have your spin prepared up or down, but now you want to measure it with respect to another laboratory axis, W prime. So, okay, back to the story. So we say, okay, with classical probability, we are in state PW, we're in state W. And then there's this quantum probability to measure W prime given by this squared modulus. Okay, let's rewrite this. So we say, okay, let's again break apart this complex square as this product of transition amplitudes back and forth. And now instead of recognizing an identity matrix, we don't have quite an identity matrix in here because there's this PW in here, but nevertheless we can, by linearity, just sort of put it in. And we see here is that matrix that appears, which a density matrix. So that's how von Neumann must have arrived at it, I suppose. And say, okay, so since we gave it a name rho, we see we have the sum over, take rho and evaluate it inside W and W. But you see, this is the definition of the trace. I should have maybe said it's obvious. So in total, this expression, the trace over H of this operator product, or operator is a big name here for a linear map for a matrix of rho with this did I make a mistake here actually? Oh no, yeah, so right, yeah, no, so it's the trace of rho with it. So we can say, okay, if I have this mixed state in represented by rho, and then have some observable, in this case it's just a projective observable, I want to say, is my system at state PW? Well, what you do is you multiply the two and trace. So that's a mathematical trick, or you can do it. And it just has.
So just can you go back to the last one, please? So you define the density matrix as CW, WW, right? Outer product W, right? In the page 34. So the thing inside the autonomic basis states would just be rho, right? So what do you have this rho PW? This is
I have some typo in here. Is that what you're saying? Let's see. I changed notation and I introduced a typo.
Yeah, the whole thing in the bracket is
rho. I switched. This is wrong here. Sorry, I switched notation in preparing this just a few minutes ago. From W, I switched notation. I should have reverted things.
I think we should just retrace the rho.
Yeah. So sorry. This is actually from here on. I'm actually switching W prime and W.
From the second one.
Yes. Yes. Yeah, sorry for that. So this is maybe, should we do it on the board? It's actually the other way around. You should take this term.
Yes.
Sorry for that. That's a silly typo. Yeah, but that's good. That's why I'm giving this talk. It's just really just to find typos in our. Okay, so yeah, I'm not gonna do this on the board now. This is an exercise. I mean, this is elementary linear algebra. You can convince yourself that the first and last experiments are actually equal. And so this is how von Neumann said it back then. And in the modern formulation, one says, instead of just writing it in a fixed basis, one says a mixed state. So von Neumann, writing it speaks of a mixture. He really said mixture. A mixture, like he means ensemble, a mixture of. Yeah, what in French we call ensemble, like in thermodynamics here. But anyway, it's called mixed states now. It's really a mixture, classical mixture of quantum states. And so the modern formulation one says such a mixed state, so the density matrix is a positive operator on the Hilbert space of trace 1. So say the subspace is no longer a linear space, it's actually a convex set. Of convex topological space, if we take topology into account, of this linear space of matrices given by those for which there exists an operator A, so that we can write them as A times A dagger. This is the definition of positivity, a Hermitian positive operator, and the trace is 1. And so the reason for this reformulation is that by the spectral theorem, in this case in its toy version, just for Hermitian matrices, finite dimensional matrices, says that any such matrix that is that satisfies this first condition has an eigenbasis in which it can be diagonalized, and in which case its eigenvalues are real and non-negative. And then the trace condition says, in addition, that the sum of these eigenvalues is 1. So the statement is that any guy in here can be expressed in its own under the spectral theorem in this form, in its eigenbasis. So that's why it's a good intrinsic description of what these mixed states should be. And so first thing we should check is that with this definition, the original pure state, so we also wanted to say that in some sense, an actual element of H is also a state. And now we have these mixed states. So we want to see that the pure states, as they're being called, those where we know exactly, basically know exactly which quantum state the system is in, are among these mixed states. And you just form this expression here, the projector onto psi. It's a positive emission operator. And it's traces one if we, yeah, in this case, I'm dividing out the norm. Otherwise, you can assume it was already in one. So these I'm going to call rho upper psi for the state psi regarded among mixed states.
What is this? Just an inclusion or what is nothing?
So the pure states actually the extremal points of this convex set of pure states. You know, if you open a book on quantum computation, they will always say the Bloch sphere at the beginning. That is a picture of this convex space. The Bloch sphere itself, the rim, how does one say, the actual sphere, this is a misnomer, right? It's the Bloch ball. So the actual 2D sphere, that is this unit sphere in H, in this case of the Hilbert space of qubits. And being convex, it now means we can take any convex linear combination of these states that fills the Bloch ball. Okay, so this brings us now to the title finally of that talk. So previously, before we added this classical stochastic aspect to the quantum theory, we were just looking at quantum circuits. Here I'm writing quantum gates, but these can be composed to quantum circuits. So we just take pure states to pure states along a unitary operator, or actually along any linear map, but in reality along a unitary map, Schrödinger evolution. But now that we say, okay, so now we want to allow for the fact that there's this classical uncertainty here, which state we're actually operating with, and that uncertainty might actually increase as we do something to the system, right? So we run an experiment, and afterwards we might be even less certain what state we're actually in, because during the experiment there's more heat being transferred to the system, there's more measurements being made, and we may not know what all the measurements actually are. So we want to have a notion now of, it's called quantum channel, of channeling this quantum information that is encoded in mixed states through some process. And it's fairly evident for Dishnia, there's a subtle here that is hidden with this adjective completely, is that we now want to be looking at quantum channels as maps that take not just pure states, but these density matrices, or the matrix, the full matrix spaces, linearly to matrix spaces, such that it observes these subspaces, these convex subsets of the density matrices. And so what would this mean? So remember, the density matrices were defined to be positive operators of trace one. So we just want to say, or we would naively just say, well, the quantum channel should just preserve positive operators. It should take a positive matrix to positive matrix, and should take trace one things to trace one. That's not actually the condition one imposes. This is going to be interesting. So I couldn't quite find out who really first. I mean, this is some ancient observation somehow, which was passed along and at some point got formalized in the notion of complete positivity. People notice that what you actually want is, you want to say, well, I have my quantum system here, and as it evolves, it certainly needs to take this positive operator to a positive operator. But actually, my quantum system, that's kind of the logic behind this, is always going to be a small subsystem of the universe, of the rest, of the laboratory. So what you say, what if I had actually taken into account more degrees of freedom than I actually care about? So what if actually I tensored my rho with the identity matrix on some larger Hilbert space, just as a placeholder for other degrees of freedom that may always be there, that we don't care about. But then still it should be the case that if you regard this as your new mixed state, as you evolve it forward with your quantum channel acting just on fine, the result should still be a positive map. And that turns out to actually be a stronger condition. It turns out there's maps that take positive rows to positive rows, but does not take all tensor products with the identity to another positive operator. So completely positive means that one requires that to actually be the case. That not only does it take positive operators to positive operators, but also all that tensor product with identity matrices. And we'll see there's, after one realized this, there's meanwhile half a dozen of equivalent reformulations of what this complete positivity equivalency means. Some of them are much more, how should one say, more insightful into what is going on. We'll see one of them in a moment. Okay, so this is just a name. So this is going to be called quantum channels. And this is like if you want to do actual real world quantum information theory or quantum computation, this is what you want to be dealing with. Yes, please.
Basically, when it's a mixed state, you mean that to compare that with the classical in algebra, you have more than orthogonal modes kind of coupling with each other. You are able to, so like in a Fourier transform, you have the Fourier mod, which is basically maybe EJ. If it's only one, it's EJ omega t. But if there are two frequencies, then you have a combination of these, and the kernel itself, that is the coefficient of the Fourier equation itself, is coupled with two states. But the operator is actually like two orthogonal.
I'm not exactly sure if I understand the question, but let me just amplify. By mixed state, as I mentioned, I really just mean what in thermodynamics is called an ensemble, a classical distribution of things. So in this picture here, so we have this set W. You might say, what is a mixed element of the set W? So a mixed element is just one element here with some probability, another element with some probability, and so forth. That's what we mean, a mixture of elements. So it's just any probability distribution on W. And now I'm just applying this not to the set basis elements, to the, in a clever way, to the vectors that these elements represent. So I'm really, at this point, I'm just looking at a probability distribution on the set of basis vectors for some basis. It's a rather, yeah. So, I mean, of course, what you said with Fourier transformation and mixing of phases all plays a crucial role in this story. But like, just for the concept of a mixed state, maybe not yet. Right, so these phases, they show up in these transition amplitudes. Okay, but maybe we can talk about this later. So, okay, so once we're convinced that we want to be talking about quantum channels, yeah, okay, let's look at some examples. So the first is, so we've seen that how pure states are among the mixed states. So we also want to see now, for this to be of any use, that the actual quantum gates, by which I mean the unitary maps, are somehow among the channels. They're called the unitary quantum channels. It's kind of obvious, but nevertheless worth highlighting. So if I do have a unitary operator from H to K, it's declared, then we get a quantum channel by saying, well, on rho, so I'll always write this rho now, which is really the notation for density matrices, whereas there may be more elements in here. You know what I mean, I hope. Anyways, for any matrix here, we just conjugate it by U. And if you look at, let's look at this in what it does in components. So suppose our rho was a rho psi, it came from a pure state, then it was of this form that it was just a projectile on psi. And so the unitary quantum channel takes this pure state among mixed states to its conjugation with U's, which means conjugation with this projector, but then we can, right? So the U's act here on these psi's and dually on the dual psi's. And since U dagger U by unitarity is the identity, I can insert it here. So I see this is the definition now of the mixed state corresponding to the pure state U of psi. So in this sense, this unitary quantum channel restricts on pure states to the quantum gate. And it does as you can see from the definitions, it does the evident thing now on a mixture. If you now feed in the mixture, so you don't know exactly which pure state you're feeding in, but each pure state in the mixture gets transformed in this way, and you get the exact corresponding mixture of unitary transforms. So this is the, if you wish, the boring, the null case. And now the important case is the measurement channel. Let's maybe hide this for a second not to get distracted. So the measurement channel was actually not written down by von Neumann. This is kind of curious. He writes chapters and chapters on the probability and the measurement aspect. But he does not quite write this formula, even though he introduces all the ingredients. it was this German guy Lüders, who seems to be known for nothing else than that, but he writes quite a bit later. So this is 51, 20 years later. He writes the article where the modern understanding of quantum collapse and the measurement channel actually appears first. So he says, yeah, for this one should not really recall, which I have further up in the slides, but I don't want to scroll now, not to lose my track here. So right, so you know that the one of these fundamental things of quantum physics is that after you have the system at state psi, you measure it, you find it to be in the classical state W. Then after that, you will discover that your system is no longer in state psi, but it's actually in the projection of psi to that subspace spanned by W, a little W. And so Lüders says, well, okay, but what if I make a measurement, and I suppose I don't actually know which measurement outcome I got. Well, but I do know by the Born rule that such and such probability I would have gotten such and such measurement. So he says, let's write this as the following rule. We take our density matrix rho and form the sum over its conjugations for the projection. So why is that the right prescription? So this is this little computation here. Let's do it for pure state, which is normalized. So in the unit sphere of a Hilbert space that is equipped with a linear basis. So this measurement channel measuring in W, it takes rho psi to this conjugation. Well, now let's expand it out. The projection operators here are these gadgets here. They project on W, this projects on W, but rho psi was itself a projection operator on psi, and I'm assuming it's normalized just to get rid of this factor subside square. And you see this expression now, which is just unwinding what it says here. But if I now bracket it differently, then I see in the middle here, this is exactly again our Born rule amplitude, no, not amplitude actually, the Born rule probability to find W and say psi. So the result of this measurement process on a pure state, regardless of the more mixed states, is exactly, if we just pull this factor out, it's exactly again the mixture that originally motivated the density matrix C through us, where we say, okay, with classical probability prop psi W, the system is in the pure quantum state W. This is kind of Lüder-Neumann reasoning, and in abstract, or I don't know, slightly more abstract form, it looks like so. So just to notice here, this is important. Yeah, I'll actually have a remark here. So before Lüders comes to this, he observes that this is not the only way to type measurement, if you wish. This, yeah, please.
Maybe ask. So what physically in the lab, how would we think about this? We measure, but we don't look, so we don't know.
Yeah, exactly.
We just want to put that uncertainty in the classical.
Yes, absolutely. That's exactly the point I'm making here. You could do something else. You could say, no, if I have a mixed state rho and I measure it, suppose I actually, well, if I'm a good experimenter, I see what I measure. So I have actually measured W now, a fixed W. Well, then I don't want to have all these probability distributions. I know I'm in state. I know I'm in just this contribution here for a fixed W on a sum. Then you can rescale. You just take what I'm trying to say is you measure fixed W, then you say, oh, this is my new density matrix. You can just rescale it to have it trace 1. And that is actually, if you do record your measurement, then that will be the actual state you continue. But now, depending on what you do, it might be you're actually making thousands of measurements because you have something that actually like a laser, something that keeps measuring something. So you don't keep track of all of them. You just want to know what happened at the end actually. Or you have some interaction with the environment that acts like a measurement if you don't actually want to. So something else is observing your system. You don't know, right? Because for instance, a cat, right? The cat comes in and so in such situations, you may not know, as this is the same case in description of classical physics. You make measurements and you may not know you actually measure it, but you say, okay, I know with which probability is something.
So
Yes.
So if you allow your system to interact with the environment, doesn't it mean that the system gets usually decoherent by?
Oh yeah, absolutely. That's what we're headed towards. Well, I'll get there. Yeah, absolutely. So exactly. So good question. So what I'm going to show next is, and this is kind of the nice crux of these quantum channels. So at this point, this is just this is just writing stuff down. This is how Lüder says, okay, this should be the measurement channel, and so be it. And it just turns out to make sense. We want to ask more deeply, maybe what's actually happening here. And it turns out a big theorem of what quantum channels is that it can all be every quantum channel, since you asked. So it turns out every quantum channel, whatever you write down, just positive, completely positive map, trace preserving, can always be written as take your original system, couple it to an environment, involve the coupled system unitarily, so let them interact, but in a coherent quantum way, and then forget what the degrees of the freedom of the environment is. And that turns out to decohere your quantum state.
So eventually, at the end, you trace out your.
Yes, exactly. Yeah, I'll show this in just a moment, how the measurement actually arises this way. Right, so this was this alternative. Yeah, here's something about these phases, but maybe we don't need this now. Right, so here actually comes exactly what you're asking for. So another important class of quantum channels is so they don't seem to have an established name. They're usually called the partial trace channels, but that's a bit of a sad name. That would be like calling the measurement channel the sum over conjugation of projectors channel. So that's the partial trace is the mathematical description, but not the meaning of it. What we can do is we can say, what if we have a system that actually is realized as the coupling of two systems? System H, the one we care about, and system B, and the B is for bath, like in the sense of thermal bath, or just environment. But it's not so good to use E as a, anyway, so I use bath, B here. And so right, we can say we have a system of which we know that it's kind of decomposed into two parts. And that's, again, of course, the generic case. You build your system in the laboratory, but it's never completely disconnected from the environment. So there's always this thermal bath around it. And then we can say, well, but the nature of these thermal environments, they don't even have to be all that thermal. The nature of any further environments, by us calling them environment, is that we may not care or not know about them in detail. Right? So we want to say, what if I have an actual quantum state of my actual quantum dot or whatever I care about, together with the quantum state of the laboratory, but I have no way of keeping track of the full quantum state of the laboratory. So I just want to kind of average over this and just see what on average the remaining quantum state of my actual system is. And so a little reflection, and maybe I don't have further motivation for this, but by a little reflection, one sees that this averaging process, well, it's given by forming the trace over the partial trace over this bath system. So I just wrote it here like so. Maybe I should have spelled this out a bit more. So you say you have this state and this coupled system. So I'm just writing a pure tensor here. So on some pure tensor psi beta prime psi, it just evaluates these betas on each other, which is the same thing as taking the trace over this B factor here. So let's see what I've. So we want to see this in action now, answering your question of how this relates to the measurement. So we're going to say now, okay, so what is it actually that happens? So what I'm telling now, this story of measurement as a decoherent quantum channel, this was a huge deal when Zurich started talking about this in 1981. For 20 years or so, there was a whole sub-community of quantum physics that was all about the decoherence effect. They thought they were seeing some deeper aspect of the theory that would somehow explain why it is that in a fundamentally quantum theoretical world, we still perceive an actual classical world. It was a huge deal. And the sense of the excitement is the following simple argument, which has its roots in von Neumann section 6, but von Neumann is really less clear here than you would think it could have been. Anyway, so here's the simple idea. What actually happens if we measure? What is this measuring thing, right? So, well, you have the system here, and to measure it, you somehow need to interact with the measurement device with some usually huge, comparatively huge system that somehow interacts with it. and somehow records, if it can, in which state the small system was, the quantum system. So if we abstract all the details, then the measurement process should be something like this. It should act on the coupled system of our actual device with this bath and should say, well, so we're measuring in this basis W, my running basis. So if the system happened to be in an eigenstate of that thing that I want to measure, so if it's actually at exactly value W, and if I have initialized my measurement apparatus in some initial state, B in E here, then, well, for it to measure means the evolution has to be such that it does not change the system. So this is called, how we call it, destruction-free measurement or something. So you want to, like in a good measurement, your system is still okay after the measurement and not blown up. So you want to say after the measurement, the small system is still in state W, but now the measurement apparatus, some pointer has moved to indicate which state W we've seen. So the big system, B, should have some states, pointer states as they're called, which kind of reflect the fact I have seen state W. So in most abstraction, right, so this initial state should go to this tensor product state W, some pointer basis BW. And so we assume now, and that assumption, the justification of this assumption fills many books, that we can find an approximately at least orthonormal basis for the bath, which contains these guys, BWs, and maybe more. So it turns out if you actually look at how this works in detail, you will not be able to find an actual orthonormal basis, but the inner product of the mixed quantum states, it becomes really tiny, really fast. That's what most of these deconvenience people actually computed. Okay, so this is an idealized measurement process of what it means to do a quantum measurement. Sort of before, how should I say, before a conscious observer or something actually doing something. It's just the interaction of two systems. But now we want to say, okay, at the end of this, we really have no clue about the system B. So we're going to trace over it, as we just said. We're going to average over the measurement apparatus. We don't care about the exact positions of the measurement apparatus. We just want to say, where's the pointer? So we trace. Okay, let's work this out. So we're going to do this. We're going to do this decomposition now of the quantum measurement channel. So we say, okay, at the beginning, we had our system in some mixed state given by some density matrix, which I'm just decomposing into its matrix elements here. So this is just a row, I guess, below it, I call it a row. Sorry, my scrolling gets really slow. This always happens on Zoom. Right, so suppose we have some mixed state, which I'm just expanding out as any matrix here. And we want to feed it through this measurement procedure. Well, first of all, we have to couple it. It was sitting in isolation, so we have to bring the measurement apparatus close by. So this simple formalism, this means we tensor with the given initial state on B. So we get from this matrix in H tensor H dual, we get an element in this bigger matrix, which is forming tensor product with a projection of this initial state. So this is, see, we have now this initial state up here and the corresponding density matrix. Well, now we do this unitary evolution that I just described here, but now as a unitary quantum channel. So it acts on the left on these guys, on the right on these guys. And if I don't have a typo again, then it should do the following. The states that where the system was in state W here get picked up by this pointer element BW. So we get, right, the system, oh, the measurement apparatus saw there was some W. But here on the right, well, the system was in W prime. So the measurement apparatus accordingly goes to this dual state W prime. And then we trace. So tracing just means we trace over B. So tracing over B means, right, we have this cat bra thing, we sum, as we had before, with this bracketing of some orthonormal basis, which has the effect of just evaluating these vectors and co-vectors on each other. So we just pair BW prime with BW. But now by the assumption, remember there was some technical subtlety in there, or some, how should I say, experimental subtlety, but to huge accuracy, can assume, and the mathematical formalism we do assume, that these are actually orthonormal. So this picks up a Kronecker delta here, which kills one of the summons in our sum. And so we wait for it to scroll. And then we see what remains is just the original density matrix summed over its projections and co-projections to these eigenstates. You see in total, the total result of this process is exactly the original Lüders measurement channel, which took rho to the sum over its conjugations with PW. But now we've realized it as this composite.
So, so this orthogonal condition, this orthogonal condition is constrained upon by the requirement of unitarity, right?
Yeah, I mean that's true. So yes. So I have a remark. Sorry, it doesn't scroll anymore. Yeah. So I have this parenthetical remark here that of course you want to convince yourselves that this assignment, which you do want to regard as being this measurement process, that it can actually be implemented by a unitary operator. So if they are orthonormal, then it's easy to see. I'm indicating it here. That it's easy to see that you can enhance this to a unitary operator. I guess if you check on Wikipedia, which maybe what you've done, they will argue from the other way around. Say unitarity demands it to be orthonormal. But whichever way you look at it, you can convince yourself there are unitary operators that implement this process. Yes. Yes, please.
So my background is more like electrical engineering. So I'm trying to relate this to how the Fourier series works.
Okay.
Where you have a random system, periodic system, so to speak, and then you decompose it. Decomposing it should be as a sum of its, the eigenvectors of all the basis vectors, which, for example, in a closed rectangular box, the sines and cosines. If it is a round circle, it is going to be like, the Bessel functions, and if it is a sphere, so to speak, it will be, other polynomials. So, but generally trying to choose which basically which eigenmodes are forcing the system to fit here. The problem is that only works if the system has a very nicely prepared coordinate system. So it's either if it's rectangular or square, but if the system is has a randomized field, then it's impossible to actually have orthonormal or orthogonal basis functions. And in that you can only approximate because you have an infinite number of them, and you just simply cannot contain all of them in the system. So you truncate, and then that determines the degree of error that you would approximate the actual system. But here you seem to suggest that the state of the system is actually not really related. There's almost there is error, but you do not quantify that error in this sense, because everything is orthonormal, right? There's no truncation, so to speak.
Yes, right. The presentation I'm giving here is the idealized presentation, where we assume this orthonormality. Oh, yeah, that's right.
So is it a requirement that is it the same requirement that we need to have this orthonormality? I think, isn't it guaranteed by the unitarity of the operations that we choose on our basis?
Let's just be clear what we're talking about. So there's two sides to this story. One is just purely mathematical aspect. That's exactly as I've shown it. There's no room for discussion, or let me know if there is. Then there's the other question, how to realize this in the laboratory. If you're an experimenter, you might say, well, you're writing down a unitary operator on paper, but now my task as an experimenter is to devise some laboratory operation which implements this. And then the experimenter may tell you, well, this is actually not so easy. I can make these off-diagonal matrix elements be real small, but I can't make them vanish. And that is another discussion, maybe which is a bit besides the point of what I want to discuss here. This is just the mathematical statement. And in fact, so let's amplify this. I'm at the end actually now of what I have to say about the quantum channels, but let me amplify a few things that I haven't maybe typed out here, but that are important. So this example here of realizing, particularly the quantum measurement channel, as this composite of first couple the system to an environment, then evolve the coupled system unitarily, and then trace out the environment. That procedure applies more generally. In fact, it's a theorem. It's not super hard to prove, but takes a little bit of fiddling to show that quantum channels among all the linear maps from matrices to matrices are precisely those that can be decomposed in this form. So every operation, in fact, every of the three steps here is a quantum channel by itself. So like in general, I mean, tensoring with any vast system unitarily evolving and tracing out quantum channels in themselves, we can easily check. And so the composite is, so no matter what the unitary evolution is, whether you think of it as measurement or something else, we'll always produce a quantum channel. And maybe more interestingly, actually every quantum channel you can write down can be realized in such a form, which gives, this is now a non-mathematical, if you will, a physical or philosophical aspect, which gives a very deep significance to what it is that happens in these quantum channels. It's, in a way, in a sense, precisely the ignorance about interaction of our actual system with the rest of the world that leads to this extra classical uncertainty on top of the quantum uncertainty, which of course makes a whole lot of sense. And then maybe as an outlook, how are we doing with time?
Almost time.
So because this would be the end of what I have to say on quantum channel, let me just make an outlook now. So what I want to do next time is I want to take this, do the opposite of maybe what the questions were hinting at. I want to go away from physics motivation and say, what if, suppose I would just, Caspar Hauser, isolated logician sitting in my cave, never seen the world, but I've thought deeply about logic. Can I find any reasons to care about? So it's easy to motivate, or fairly easy to motivate the fact that in quantum physics, where we have no cloning theorem and no deletion theorem, that my what used to be sets of states in classical physics should be linear space of states, and the quantum gates should be linear maps. It's kind of fairly straightforward to motivate. But why would I, if I hadn't read von Neumann and followed the literature in the 100 years since, how would I ever get the idea of tensoring this vector space now with the dual vector space and start operating on this? We'll observe next time that this operation of taking any existing spaces like the H here and tensoring it with B, tensor B star, is an example of a monad or a comonad. And then all the operations, or most of the operations we've seen here are, how should I say, not implied, but are operations that one naturally considers in such a context. In particular, the trace operation here turns out to be the co-unit of the quantum state comonad. So we'll see that there's a formulation that takes in particular this decomposition of any quantum channel as a unitary followed by a trace and reformulates it as a monadic transformation. And interestingly, this implies a whole lot of things. For instance, there's a general theorem that tells you if you have monad transformations, monad transformers, then they act on the Kleisli morphisms. So there's some other abstract constructions of these monads, and we'll see the Kleisli morphisms or the co-Kleisli morphisms for this quantum state monad are exactly the quantum observables, and the action of these monad transformations on these Kleisli morphisms comes out exactly as Heisenberg evolution, as the eponymous foundational aspect of quantum dynamics, which tells you that how quantum observables evolve as the quantum system evolves. So that's a bit of the idea for next time. And that will be what I have to say today, unless there's more questions.
Great. Thank you, Urs. Any further questions for Urs?
Quick question. So I'm aware of, familiar with SVD, with singular value decomposition in linear algebra, which says that any matrix can be decomposed, so to speak, into like a U on the left and a V on the right, and in the middle we've got this matrix of orthogonal bases. This looks very similar to.
No, it's actually the special case where you just need the middle diagonal matrix. So this is what's called the spectral theorem. So since we're talking about very, how should one say, very well-behaved matrices, Hermitian matrices, or you might say if we were doing this over the real numbers, it would be just symmetric matrices over the complex numbers, the Hermitian matrices, positive Hermitian matrices, and they always have a diagonal form, some eigenbases, yes.
Okay.
And that's what we're using here. So it's in a way an even simpler special case of what otherwise would need the signal value decomposition. Yeah. Where was it? I'm trying to scroll, but I can't scroll.
Any other questions?
Can I ask maybe in this CQTS score, where does the largeness of the buffer come in?
Yeah, that's a good question. It does not in this mathematical description. It is just the, how would you say, the physics motivation or justification for taking the trace. The trace means just for you do average over that system. And now if your system is small, it's just a qubit, there's no good reason for doing that. In the lab, you could just take care of it. But if your system is large, you have no chance, that's why you average. So that's kind of the justification. I should also add here that in this theorem that allows you to express every quantum channel as being of this form, evolve a coupled system deterministically, and then forget something, it's actually, now I hope I get the numbers right, it's actually known that you can, the bath doesn't have, there's a bound on the size that the bath has to have in order that you can realize your channel. I think
you use dimension or something of the Hilbert space in any dimension. What do you mean by size?
Yeah, for instance, I hope I'm remembering this well now. It's for instance, if you just have Hilbert space of dimension 2, just qubits, and you want to just realize quantum channels on single qubits. So unless I'm misremembering now, it's actually sufficient to couple it to just one other qubit, to take this bath to be just one other qubit. This is no longer the case. So in general, I think the size of the bath scales quadratically with the size of the system that you need, the minimal baths that you need to represent every quantum channel. So in practice, you don't actually need this bath to be super huge, depending on your system.
But it is satisfying in the world we see, right?
Yeah, exactly. Yeah, it is more than, yeah, exactly. It's more than satisfied. Yeah, but for the practice of quantum computation, so we'll see next time that, so this monad we're dealing with here is actually both a monad and a co-monad for those for whom this means something. It's actually Frobenius monad, but this transformation here, this monad transformation, which is the tracing out, will only be a homomorphism of co-monads, whereas the preparation will only be a homomorphism of monads. So when it may happen in actually implementing a given quantum channel in your suppose programming language or something, it may be you do want to encode it in such a way that you say, okay, suppose I do know my system. So you describe your system as being coupled to something, and then evolve with units therein in trace, just to implement the measurement process. And for that, you do want to find small baths that are sufficient for realizing that process. So this is not so much a reflection of the physics, if you will, it's just a modeling aspect. Maybe that was cryptic. Now I can try to say this better next time.
So just
Yeah.
a follow-up to Greg's question. So can't we do this more perturbative? Can we have a perturbative treatment? Because as we do a measurement, we have quantum fuzziness. So there's all fuzz that goes due to the measurement that we're taking on our system, right? So can't we have this like as we do in quantum field theory, right? So you have a free density matrix plot some interaction times the Bach density matrix.
The interaction is not encoded in the density matrix. If you want to talk, so this seems a bit of a random comment now, let me say, but what you should ask is here in this interaction process. That's the process where one can ask for something to be. There's no sense in which a density matrix is a free part. The density matrix is just kinematical data. There's no process, no interaction. The interaction happens in this case here. It's the unitary operator on the coupled system. And if you want, you can play with this and expand this around some base map. At this point, there's really no, I don't know, no need. Yeah.
Right at the start, you suggestively called W worlds.
Yes.
How does that, and then now you've got this like really honest description of like a larger field of space. You traced out everything's unitary, and you've got a classical mixture of your worlds left at the end. So I don't know, were you going somewhere with naming the basis states worlds? Does that fit nicely into the honest description you're giving them?
Yeah, I do think so. Actually, in this draft, in other chapters, we expand on this quite a bit, relating the measurement process to model logic. So that is the worlds that people talk about when they speak of many worlds in quantum physics. They say they make some measurement and they speak about the world branching in either of these branches, and that's at that point. I mean, people speak so loosely in this context that it's a bit hard to pinpoint. It seems they always imagine, they try to imagine the entire universe as being the system that they consider. They like to speak in really grandiose terms. But what it comes down to is just they imagine some Hilbert space with some basis, and at every measurement, it collapses to one of these base elements, and these are the observed worlds. I think that makes a whole lot of sense if one doesn't read the term world in this very ontological sense. You shouldn't think about universal. It's just kind of the world that we happen to find ourselves in, right? So we make a measurement, right? I want to say, right? So what is in this cup? I want to say what is the world we live in? Oh, it contains hot tea, right? So it's a very mundane thing, and in this sense, I think worlds is actually a good name for it.
But you say observe worlds, you actually take it distinct from what they. Yours is perception, is what you observe. When they say world, they actually mean ontological thing.
I do think in the end they all talk about this. I actually went through the trouble of reading Everett's original discussions. He talks about exactly these kind of processes. You have a system, you measure it, you find it in some state or not. Yeah, but anyway, so the W comes because in some other chapter we discuss in much detail the monadic realization again of the measurement process on pure states, and we prove, but it's just the fact that it follows that it's exactly a linear, in the sense of linear logic, a linear analog of the classical rules of classical epistemic logic. And in classical epistemic logic, it's an old tradition they speak of possible worlds. So this originates in mathematical philosophy, where people were trying to look for formal logical calculi which allow them to speak of not just of a single reality, but of possible worlds. So that it's a logic where you don't just say proposition is true or false, but when you can say it's possibly true in some world, or it's necessarily true in all worlds. That's exactly the terms that dates back decades, centuries ago, inside years. And then I think rather independently from the many worlds of the quantum physicists, these classical model logicians, we're talking about worlds in much the same sense. And it's in fact used a lot these days in when you model, for instance, model logic turns out to be actually used in the modeling, in the computer scientific modeling of what's called distributed systems, where every agent, every computer in a network has to reason about what's going on. And in that context, so the formal logic these agents use is a form of model logic. You know, they have to make assumptions about what the other agents are doing. They have not full information, but they do have information about what all the possibilities are, right? So, you know, every agent has maybe 10 states, and now you want to make a decision based on your knowledge. And you say, well, you can maybe determine that it's possible that one of the other agents is in state 2 or something. You don't know precisely. And in that sense, again, for that agent is reasoning about its perceivable worlds, just in the mundane sense of all the possible configurations that it's aware of. You know, it's not a metaphysical statement about God creating the universe. It's just about what are the configurations that exist.
So in other states that we can take the view of this world as to be sort of a collection of ensembles, right? With different microstates.
Yeah, that's true. Yes. Yes, that's true. And that gets us, in a sense, back to exactly what I just said. There's also a classical notion of possible worlds, yeah, which is exactly this. If you're a thermodynamical classical theorist, you also never know exactly which world you actually inhabit. Isn't this world that I'm inhabiting, does this atom move with velocity such and such in this direction in a gas or not? You don't know, right? So you're reasoning about an ensemble of many worlds, even though people weren't so confused about this that they felt they needed to invent this kind of terminology, but it's really the same. Anyway, that's the reason, but it's just a W. I used to, at the beginning, we used to call it B for basis elements, but B is already overused to too many other things, and then W. And yeah, so this analogy between classical and quantum model logic actually works rather neatly. Anyway, that's our W, yeah. But you're right, maybe your original point was in this sense, there's this small world here of H, but the world is actually larger. Was that maybe your point with the bath? You realize there's actually many more worlds.
So yeah, and then you have, well, I mean, I'm just checking that you weren't, trying to think about worlds branching like some people do. That's it. But
So,
which are not. Right.
well, I mean, let me, if I could scroll now. Yeah, this is a pain. Zoom freezes my computer. But actually, we do have something to say about this branching. I'm not sure if I can get there now. Like, there's some theorems we proved using just this model logic, which arguably reflect exactly. I cannot go there.
Yes, so perhaps you can come back next.
Yeah, maybe next I can go to this. But there's some other statements that one can make that arguably capture a lot of what Everett is concerned about in his thesis. Yeah, let's do it next time.
Okay, any other questions? Okay, if not, let's thank Urs again. Thank you, everyone. We look forward to the next talk on Wednesday.